if you recall from dynamics, we talked about Newton's first law, and it was nicknamed the law of inertia. So if you remember, inertia again was, an object in motion tends to remain in motion, or an object at rest tends to remain at rest. That's what inertia is. It's whatever an object is doing, it's going to tend to stay there. And the more inertia something has, the more difficult it is to either get it moving or to stop it from moving. And so when we take a look at rotational inertia, which more commonly is actually called the moment of inertia, because moment actually means something that's spinning, then we're talking about an object that's rotating about an axis. And of course, if it has rotational inertia, that means that object rotating about that axis is going to tend to keep rotating unless there's something outside of it that stops it. So another way we want to think about this is that if this object is going to resist a change in rotational motion, that's its rotational inertia. That's kind of what we want to think of as rotational inertia, is how much object is going to resist a change in rotation. So that could be starting or stopping rotation. Okay, so the more inertia we have, the more difficult it is to start or stop rotation. So that's the main way we want to think about rotational inertia, right? So if I want to start or stop rotation, well, just like a force is needed to change the linear state, right? If something's moving across the floor, then you need to apply a force to stop it. So we need torque to change rotational state of motion, right? We need an outside force to change that rotational state of motion. Now let's talk about when is there more rotational inertia for an object versus less, okay? So rotational inertia depends on mass, but it actually depends more on the distribution of the mass along the axis of rotation, or how it's rotating, okay? So basically, if there's a bigger distance between the bulk of the mass and the axis at which it's rotating, the greater the rotational inertia. So it's much easier to think of this in terms of an example. So when we have our masses all the way back here with this guy, we know that this is the kind of situation where it'd be a lot more difficult to rotate it. And then once you rotate it, it's a lot more difficult to stop its rotation. And that's because its mass, this is the axis of rotation right there, which we could also call the fulcrum. The mass is so much further away from that axis of rotation. So if I take those weights and I move them in where they're not as far away, and they have a much shorter distance between the axis of rotation and where the mass is, that's going to be a lot easier to rotate those objects. So it's the same mass, right? The mass didn't change. We didn't add more weights, but just moving those weights to closer to the inside, closer to where this guy is going to rotate, these weights makes it easier to rotate, also makes it easier to stop it rotating once you get it rotating, okay? So that's really the most important part about rotational inertia, is how is the mass distributed about the axis of rotation, okay? So if it's closer to the axis of rotation, then it's going to have smaller rotational inertia, meaning it's easier to get it rotating and easier to stop it from rotating. And when the mass is further away from the axis of rotation, it's going to have a bigger or a greater rotational inertia, which means it's more difficult to get it rotating and more difficult to stop it from rotating once it's started. Okay, Rotational inertia is also greater when the mass actually, that's what I just said. But when all the mass of an object is concentrated at the same distance from the rotational axis, so basically we could have like a disk that's solid, or a disk with the same mass, but all the mass is on the outside and then it's just hollow on the inside. Well, again, even though it's the same mass, this one, its mass is more distributed throughout, so that one's gonna have less rotational inertia, where the hollow disk is gonna have greater rotational inertia, because the same mass is distributed, but only on the outside, so it's further away. More of the mass is further away from the center, or from the axis of rotation. Okay, don't get me wrong, it's not an easy concept to get, but the more we do it and the more we think about it, the more we will get it. So again, just have to think, if more mass is farther away from the center, from where it's rotating, it's going to be more difficult to rotate it. More difficult to rotate means greater inertia, rotational inertia. Okay, so we have an equation for rotational inertia, and this is for one very specific situation. So that's basically if we had like the mass on the end of a string or something, or mass on the end of a baton or something like that, and then we want to rotate it around, the rotational inertia there would be mass times r squared. That's the radius of the circle that it's going in. Okay, so that's something like that, or basically the rotational inertia, something like this, like a hoop or a ring or something like that, would be mr squared. But then when you start getting the mass in different sort of places, then equations do get a little bit different, and we'll look at a few of those. But this is the most basic form of rotational inertia equation. Okay, and so this is where I is the moment of inertia, or the rotational inertia. Its units are kilograms times meters squared, basically just what it's made up of. Okay, there's not a special unit for rotational inertia, where m is, of course, mass, and r is the distance from the axis of rotation, and then we square it, so the units become m squared there. Okay, so that is the most basic form of rotational inertia. But again, that's only if the mass is distributed at the very end, at the very farthest point from the rotational axis. Okay, so that's when we have I equals mr. But we actually have, for various objects, a bunch of different equations for a moment of inertia. And you will be given, if it's not like a hoop or something like this, or something on the end of a hoop or a string or something like that, then don't worry, you will be given the equation for that. Okay? So anytime that we're talking about a cylinder that's maybe solid, right, then you will be given the equation for that, because you're not expected to just know all of these equations. So if we have like a solid cylinder, that's going to be way different than a hoop, right? And so that's I equals 1/2 ml squared, where L is the length of the cylinder. Okay, so there's a bunch of different ones. Here's just a few examples here, and then of course it depends on what your rotational axis is. Because this is the situation that I just kind of pointed out here. This is when you're rotating at about this kind of center. Okay, because that's one place in which you can rotate it about. But what if I want to rotate it along its much smaller side? Then that's actually going to have greater rotational inertia, because it's going to be farther away. Okay, the mass is farther away from where you're rotating it, and it has a whole different equation. Okay, so again, anytime you're given one of these situations, you will be given the equation. The only one you were expected to know is this I equals mr squared, and again, that's for a hoop or a ring, or even like in the next example we're going to see batons with mass at the end. And of course, if this is just going around like that, then about like an axis of rotation, that's kind of the same thing for that, right? Because if you think about this guy spinning around its center right there, it's gonna blur together to make it look like a hoop, right? So that would also apply to that situation. Okay, but like I said, let's do the example. So here we have a majorette twirling at a baton made up of 4 spheres fastened to the ends of very light rods. So we're gonna basically, the reason they're saying that is they're saying, okay, well, we can ignore the mass of the rods because that does affect rotational inertia, absolutely. Because there's some mass in here and in here that would affect rotational inertia a bit. But if they're light enough rods, then it won't really affect it so much that we actually need to account for it in our calculation. Okay? So each rod is 1 meter long, which means if I want to find the rotational inertia of the baton about the axis labeled O. Okay, so that's kind of the middle of this cross section. Okay, so there's O right there. So then I know all of these masses are 0.5 meters away because of course each of the rods are 1 meter long and O looks to be in the center of all of those. Okay, so something really important to take a look at there. So all of these are 0.5 meters away from the center of its rotational axis. So this is going to be the greatest moment of inertia, spinning it in this way. Reason being is because if you spin it in this way, everything with mass is as far away from that center as it can get. In part B, we're going to find I of the baton about the axis label O prime. So that's this axis right here. Okay, so there we go. There's O prime or O tick or whatever. And so it's, in this case, really, sure, these guys are spinning around about the axis, but they kind of cancel each other out. So we don't actually have to look at them. And then we only have these 2 masses that are spinning that are far away from that center of axis, from where it's spinning. So rather than having 4 masses spinning around, we really only have 2. So that's going to have a lesser moment of inertia or rotational inertia. Okay, so the one with the greatest rotational inertia is definitely scenario A here. Okay, so here's scenario A, here's scenario B. And so we're going to have to figure out how to find the rotational inertia for A. Well, really, all I have to do is I have to look at the rotational inertia for each of these masses, right? Because each of them are going to have a special rotational inertia. You add them all together because they're all moving at the same time. We have the total rotational inertia, okay? And this is a situation in which we use I equals mr squared because, again, if you twirl this thing, it's going to look like kind of that ring, that hoop, right? All the mass is concentrated at the very end, as far away from the axis of rotation as we can get. Okay, so that's how we know we're going to use that. So let's do it. So for A, we need the total rotational inertia. Well, one other thing I forgot to say, we have 2 masses, capital M, that are 0.3 kilograms. So I'm going to call that IM. And I capital M, and then of course we have our 2 smaller masses with a lowercase m. So that's what I'm gonna do. So really I have 2 inertias with the capital M, 2 inertias with the lowercase m. So I'm gonna add all those together. So if I want the total rotational inertia, really I just need to take the rotational inertias for the capital M's. I'll have to multiply that by 2. There's 2 of the rotational inertias for the smaller masses. And that's how I'm going to do that. How do I get rotational inertia? Again, we just figured out it's mr squared. So of course, capital M for the bigger masses times r squared plus 2 times small m r squared for the smaller masses. Okay, pretty easy, right? The bigger masses were 0.30 kilograms. Again, we figured our radius is 0.5 meters. And then the smaller masses are 0.2 kilograms. And we find our rotational inertia to be 0.25. And remember, the units are super easy, just kilograms times meters squared, as that's really all we're doing. Taking mass, multiplying it by distance squared. Okay, and there we go. There's our rotational inertia in part A. Okay, let's take a look at part B. Now we want to find the rotational inertia I of the baton about the axis labeled O prime. So again, that's this guy right here. And really what's spinning around the axis is these guys. Again, these guys are technically spinning, but the weight, the mass of them is always balanced along that axis. So we don't actually need to account for that, which is really, really nice. So we are going to take a look at these two big masses. So really we just have the rotational inertia for that guy and the rotational inertia for this guy, and we can just add those together. Well, that's not too bad because they're exactly the same thing. So really it's just half of what we did in this first part, right? Where it's 2 times those rotational inertias, which is 2 times the mass times the radius squared. So nice and easy. And that, of course, gets us a smaller rotational inertia, which is exactly what we would expect because there's less mass around the axis, right? Or far away from the axis about which we're rotating. That's 0.15 kilograms times meters squared. And there we go. Okay, so that's how we calculate rotational inertia. And remember, the bigger the rotational inertia, it just means that it's going to be more difficult to rotate and more difficult to make it stop rotating. It just needs more force to make both of those things happen. That's what bigger rotational inertia means, okay? So I'm going to ask you a question about something, because again, we want to take another look at if mass is concentrated just on the outside versus if it's concentrated throughout the whole thing. So think about this. Which of these will roll down the incline with greater acceleration? Basically, which is going to reach the bottom of this incline first? The hollow cylinder or the solid cylinder, if they have the same radius and mass, okay? So they still have the same mass. That's really, really important because obviously if they have different masses, well, then we're talking about something completely different. But if they have the exact same mass, the only difference is this guy just has its mass all concentrated on the outside, and this guy just has its mass throughout the whole thing, right? Which one is going to reach the bottom quicker? So again, which one would have more rotational inertia and which would have less? And then consider the fact, what does that mean if something has more rotational inertia? Because usually you're like, oh, something has more rotational inertia, so the one with more is obviously going to hit the bottom first. Nuh-uh. Remember, something with more rotational inertia means it's harder to get it spinning. And so, as you may have hopefully guessed by this point, the one with the mass just on the outside, that's the one with more rotational inertia. What does that mean? It means it's difficult. It's more difficult to get that guy spinning, that green hollow cylinder spinning, than it is for the blue solid cylinder. Okay, so that has the greater, I guess that's, no, what do I want to do? So remember, this guy has the greater rotational inertia, okay? So that means it's more difficult to move. Okay, so just like the thing with less mass, if it was given the same push as something with more mass, it would move faster. not necessarily due to gravity, but it would just be easier to move something with less mass. In this case, it's not necessarily easier to move something with less mass, it's just how the mass is distributed. It's all about how that mass is distributed, okay? So here's the answer. The solid cylinder is going to reach the bottom first. And I've already kind of explained why, but here's just like it in fancy words. So the cylinder with the smaller rotational inertia will move faster, because with the one with greater rotational inertia requires more time to get rolling, okay? Inertia is kind of the measure of laziness, okay? More inertia means it's more lazy. Doesn't want to move. It takes a lot more work to get it moving, okay? So, the cylinder with the mass concentrated further from the axis has the greater rotational inertia. Again, because the axis about which it's rotating is here in the middle, and all of this guy's mass is as far away from it as you can get, whereas this guy has the mass on the outside, but also has some mass pretty darn close right there to the inside as well, right? So it has mass, some of that mass on the outside, but some of it's on the inside, which mass on the inside will have a much lower rotational inertia. So altogether, it has smaller rotational inertia. So the green one would take longer to get going, and the blue one would definitely win that fight. Okay? Okay, let's talk a little bit about rotational inertia and how it applies to gymnastics. Because if you think about gymnastics, it starts to become so crazy when you really think about what gymnasts do to rotate themselves. Okay? So the human body has 3 principal axes. So that's basically just an axis is what you can spin about, right? So we have the one like this one that basically cuts our body in half here, where like the left side and the right side. And that's going to be the easiest one to rotate about. Like pretty much anybody here could jump up and rotate in that direction, like left to right, right to left, as they're doing so. But it's much, much more difficult to then rotate in the X or Y axis, basically your body front to back or side to side. It's much more difficult to rotate in that way. And why? That's because your weight, your mass is more distributed. It's farther away from those rotational axes. Okay? So the Z-axis, again, has the smallest rotational inertia, so it's easiest to rotate about that axis. Yeah, that's basically all I have to say. So that's why when gymnasts do what they do, it's pretty crazy, okay? And I don't want anybody to be like, oh yeah, but like it's actually not that difficult when you rotate them around the y-axis, because you know that's just called a somersault and everybody can do a somersault. No, guess what you're doing with your mass in that point? You are making your mass closer to your center of gravity, and therefore you're actually making it easier. So really, I'm talking about when y is your rotational axis and you are staying as long as you can, making that rotation is incredibly difficult, which just makes it more interesting what gymnasts can do, which is crazy. So your rotational inertia is much greater when your body is fully extended. Okay, so hands up, everything like that. So like this guy, let's see. We'll see he's even like tucking his arms in and kind of has his knees a little bit bent, because again, that just makes it way easier to rotate. But while he's on this swingy thing, and see like all his hands, his arms, his legs are all stretched out. That takes an insane amount of rotational inertia to get that going. So a gymnast's rotational inertia is up to 20 times greater when swinging in that extended position than when you are in a somersault position. Because again, when you're doing a somersault, what are you doing? You're making all your mass concentrated more around your center of gravity than as if you are just standing like you normally would. Okay? So, yeah, definitely have some respect for what gymnasts do, because it's crazy that somebody can get their body to move like that. Okay, let's just talk a little bit about torque and how it applies to rotational inertia, and then we will be done. Okay, so of course we know to get something started or stopped in rotational inertia, we need force. If we need force, and we're talking about rotation, we need torque. Okay, so a particle of mass m rotating in a circle of radius r at the end of a string, and a single force acts on it, the torque that gives rise to that angular acceleration, well, we know torque is r times f, the radius times the force needed to give that torque, right? But force is equal to mass times acceleration. However, we're talking about tangential acceleration here is what we would be talking about with that ma. We found out tangential acceleration is r times alpha, alpha being our angular acceleration. Therefore, we substitute that all in. We substitute mr squared times, well, mr alpha into r times m times r times alpha, blah, blah, blah. Anyways, oh goodness. You get this. You get torque equaling mr squared times alpha, your angular acceleration. Wait, what's mr squared? Well, isn't that rotational inertia? So basically, then we can even take this part right here, say, oh wait, that's rotational inertia. So then I can just plug in I for that, and I get this lovely equation. So sometimes you need to find the rotational inertia. Sometimes it's given to you, right? If you're looking for the torque needed to make something accelerate in a rotational fashion, okay? And then of course we're multiplying that by angular acceleration. So if something's moving in a circle, or rotating in a circle, but it's not accelerating, then we won't have any torque. Okay, so remember in the last lesson, we did say torque is proportional to angular acceleration. And here now I am showing you how it is proportional. Isn't that so excited? So this is basically the rotational equivalent of Newton's second law, which of course is net force is equal to mass times acceleration. Okay, and this is technically net torque. And it's a little bit different because we have to, again, add in the fact that it depends on how mass is distributed and where you're applying the force on something. So anyways, but that's how we relate torque to rotational inertia. It's rotational inertia times your angular acceleration. Okay? Okay. We're just going to do one example, and then I'm going to be done, if you can believe it. Okay, so I've got a solid steel wheel. Has a mass of 15 kilograms. Okay. This one's going to throw a lot of information at you, so I'm going to write it down as we go. 15 kilograms mass. Great. Has a diameter of 0.44 meters, so of course we usually want radius, so we should probably divide that by 2, so its radius is 0.22 meters. It starts at rest, okay, and then we're going to make it rotate at 8 revolutions per second. So if we're talking about angular speed, angular velocity, it's starting from rest, so 0 radians per second, okay, so that's our initial speed. And then final rotational speed is going to be 8 revolutions per second. Problem is we don't want revolutions per second. We always want radians per second. What do? Remember, we just multiply that by 2 pi because 1 revolution is 2 pi. And so 8 revolutions is going to be 2 pi times 8. And that's going to give us radians per second. So that'd be 16 pi, or if we want to actually calculate that, that'd be 50 radians per second. I'll just be using 16 pi in calculations because that'll get me the proper calculation and the proper number, but just so you know, that's 50 radians per second, or about 50, obviously, I rounded that. Wait, what else do we got? And that happens in 15 seconds. What happens starting from rest to going to 8 revolutions per second? That happens in 15 seconds. Okay. And then we're given the equation for rotational inertia. We know this one, it's not one where all the mass is on the outside. We have mass kind of throughout. Okay, and this is basically true for any cylinder or any disc or anything like this where it actually has mass throughout and not just on the outside. It's usually 1/2 m times r squared, and that's what the rotational inertia usually is. But as promised, you get that equation if it's not just something on a mass on the end of a string or a rod or something, or it's not a ring or a hoop. Okay, so we want to know, what torque must be applied to the wheel. Okay, so if we look back at this last page, we see torque is equal to rotational inertia times angular acceleration. We don't have any of those, so isn't that fun? But it looks like we can find them pretty easily. How are we going to do that? Well, rotational inertia, we were given that, right? That was 1/2 mr squared. Rotational acceleration might be a little bit more difficult, but remember, you can use basically all of your calculations from kinematics, all your acceleration formulas, and then just sub in alpha for A, omega for V, and theta for D. And so there is an equation that I'm going to use there. Oh, not A. Alpha is equal to change in speed. So final minus initial divided by time. We have that, right? We have final and initial rotational velocity. We have time. So we're going to be able to find that pretty easily, okay? So you can find that first, or if you're like me, you can just do it all in one kind of situation, in one go. And that's what I'm going to do. So there we go. There's our rotational inertia. 1/2 mr squared. Our angular acceleration will be the change in angular velocity divided by time. Okay, and again, if you want to find those separately first, you can. Now, I need to remember everything. So that's 15 kilograms. R is 0.22 meters. Don't forget to square that. And then change in rotational velocity, and that is 50 radians per second minus 0. Of course, you don't have to put the minus 0 in there if you don't want to, as long as you're showing the actual change in rotational velocity in your original equation. Okay, beautiful. Multiply all those together. What do we get? We get 5.5 newtons times meters. Okay, or meters times newtons. Remember, it can be either. It doesn't really matter which one. And there's our torque needed. Yay. Okay, finally, B. If you apply the torque by wrapping a strap around the outside of the wheel, how much force should you exert on the strap? So you have the strap here, and you are going to pull it, and that's going to make this wheel go, okay? So we need to apply some sort of force. Okay, so let's go back to our original equation for torque. What was it? Remember, that's torque is equal to R times the perpendicular force. And in this case, we are going to assume that we are only going to apply a perpendicular force. Remember, that means perpendicular to the radius, okay, at this point. So if this is here and this is where the radius is, I'm going to assume that I'm applying that force in the perpendicular direction here. And if I don't, then that's just a silly thing of me to do. So that's what we're going to assume, that we're applying that perpendicular force. Look at that. We have torque, we have R. We can absolutely find our force without a problem. And we get 25 newtons, which really isn't too much. It's not too bad. Somebody could absolutely do that. Okay, that's rotational inertia. You guys, this is a difficult concept, okay? It's interesting, don't get me wrong, but it is a difficult one. So don't beat yourself up too much if you're not immediately understanding it. If you are in my class, I'll post a few other YouTube videos that kind of just show some more stuff about rotational inertia. If you can't be in class to see any of the demonstrations I get to do in class. So again, if I am your teacher, make sure you ask me for those. If I'm not your teacher, well, just search up rotational inertia, and you will definitely get some videos on demonstrations, which is really just kind of where it's at in understanding how it works.